Hello everyone, welcome back to another video from my channel. In our last video we discussed about the statics of a particle, finding unknown forces when a system is in equilibrium, solving static problems involving weight, tension and pulleys, and the concept of limiting equilibrium. Today we will be looking at the last chapter of Mechanics 1, which is moments. So far you have looked mostly at situations involving particles. This means you can ignore rotational effects. In this chapter, you begin to model objects as rigid bodies. This allows you to consider the size of the object as well as where forces are applied. The moment of a force measures the turning effect of the force on a rigid body. It is the product of the magnitude of the force and the perpendicular distance from the axis of rotation. So the clockwise moment of F about P here would be the magnitude of F multiplied with the perpendicular distance, which is D here. In the diagram above, the distance given is perpendicular to the line of action of the force. When this is not the case, you have to use trigonometry to find the perpendicular distance, where in this case the clockwise moment of F about P is equals to F multiplied with d sine theta, which is the perpendicular distance from the force. Now let's talk about resultant moments. When you have several coplanar forces acting on a body, you can determine the turning effect around a given point by choosing a positive direction, either clockwise or anticlockwise, and then finding the sum of the moments produced by each force. The sum of the moments acting on a body is called the resultant moment. For number 4, the diagram shows a set of forces acting on a light rod. The resultant moment about P is 12.8 Newton meter clockwise. Find the value of x. Before we solve this, we must know what does the direction of anticlockwise and clockwise mean. For example, if we have a clock, and as we know that the minute hands, the second hands, and the hour hands start moving in this direction, and this is the clockwise direction. However, if you try to move it in the opposite direction, which is like this, then this will be anti-clockwise, which is opposite to the direction of how the clock hands move. So in order to solve this problem, we have to dissect the forces. So acting in the upward direction, we have 6 newtons and 12 newtons. And since they're acting upwards about P, we can say that this will have a relative motion in this direction similar to this. So since these are in this direction, this is the clockwise motion. So we can say that taking moments about P, moments which is in the clockwise direction, therefore the clockwise moment is going to be equals to force multiplied with the distance. So in this case we have 6 newtons and the perpendicular distance is this, which is going to be 2x plus 3x plus x, which is 6x. So 6 into 6x plus the effect of 12 newtons, which is plus the effect of 12 newtons. So 12 multiplied with the perpendicular distance, which is x meters. So x, and therefore we have 36x plus 12x, giving us 48x Newton meters. And taking moments from P again, we can find the anti-clockwise moment, which will be caused by the 10 Newton force, which is acting downwards. Therefore, as you can see, if you allow this force to move, it's going to cause a rotation in this direction, which is the anti-clockwise direction. So the anti-clockwise moment is going to be force into distance, which is 10 newtons multiplied with 4x. So 10 into 4x giving us 40x Newton meters. So therefore, we can find the resultant moment about P, which is in the clockwise direction. Therefore, 48x minus 40x is going to be 12.8 Newton meters. So subtracting the terms, we get 8x is equals to 12.8. Therefore, the value of x is equals to 12.8 divided by 8, which is going to be 1.6. And this is our answer. And now let's talk about the concept of equilibrium. When a rigid body is in equilibrium, the resultant force in any direction is 0 newtons, and the resultant moment about any point is 0 newton meters. You can simplify many problems involving rigid bodies by choosing which points to take moments about. When you take moments at a given point, you can ignore the rotational effect of any forces acting at that point. So let's do some questions from exercise 8C from the M1 book. For number 6, a uniform rod AB of length 4 meters and weight 20 meters is suspended horizontally by two vertical strings attached at A and at B. A particle of weight 10 newtons is attached to the rod at point C where AC is 1.5. So therefore we can construct the diagram, which will look something like this. So this is going to be AB, which is uniform, meaning that the center of gravity will be exactly at its midpoint, which is 20 newtons. And since it is 4 meters, then we can say that this distance is going to be 2 meters and this will be 2 meters as well. And we also have two vertical strings attached to A and B, meaning there should be tension here and a tension here. And since a particle of weight 10 newtons is attached to the point C where AC is 1.5, so we can say this is C and this is going to be 10 newtons, which is the weight of the particle, and this is 1.5 meters. So we have to find the magnitudes of the tensions in the two strings. So let's assume this is TA, which is the tension at A, and this is the tension at B. So we can take moments from A, and if you construct the diagram from the perspective of A, you can see that there's only 10 newtons acting and 20 newtons acting. Similarly, tension at B. So therefore, we can ignore the effect of tension of A because the perpendicular distance from tension at A is 0. So this is 1.5, this is going to be 2, and the whole thing is going to be 4. Therefore, tension at B multiplied with 4 is going to be equals to 1.5 into 10 plus 2 into 20 newtons, because this will produce an anti-clockwise moment due to tension B, and the weights will cause a clockwise motion or moment due to the downward position of the weights. Therefore, the total anti-clockwise moment will be equals to the total clockwise moment. Therefore, tension at B will be equals to 15 plus 40 divided by 4, which is going to be 13.75 newtons. And to find out the tension at A, we can resolve vertically and say that since there are only 4 forces acting, which is something like this, so as the system is in equilibrium, we can say that the total upward force is equal to a total downward force. Therefore, we can say that tension at A plus tension at B is equal to 10 plus 20, which is the total downward force. Therefore, tension at A is equal to 30 minus tension at B, which is 13.75, which is going to give us 16.25 newtons. For number B, it is said that the tension at B is 1.5 times the tension at A. Therefore, we can assume that the particle is closer to the point B than to A because the tension is greater due to the increase in clockwise movement, and this is going to be tension at A because this is A, and so C will be somewhere here, which has a weight of 10 newtons. Similarly, there is weight of the beam or the rod itself, which has a weight of 20 newtons and at a distance of 2 meters, and the point C is x meters from A, which we have to find. So resolving vertically, we can say that tension at A plus tension at B is equal to the downward force, which is 20 plus 10, So tension at B is going to be 1.5 times dA equals to 30. So therefore 2.5 dA is equal to 30, meaning tension at A will be equals to 30 divided by 2.5. So tension of A is equals to 12 newtons. Therefore tension of B will be 1.5 times 12, which is going to be 18 newtons. So we can take moments from A. This is going to be 2 meters, which is 20 newtons. And this is 10 newtons, which is a distance x from point A. And here we have TB, which is 18 newtons at a distance of 4 meters. So therefore, the total anti-clockwise moment will be equals to total clockwise moment for 18 into 4 is going to be equals to 20 into 2 plus 10 into x. So solving for x, we have 18 into 4 minus 20 into 2 all divided by 10 to get 3.2 meters. And this is the new distance from A. For number 8, a uniform plank AB has length 5 meters and mass 15 kg. The plank is held in equilibrium horizontally by two smooth supports A and C as shown in the diagram, where BC is equal to 2 meters. For number A, we have to find the reaction on the plank at C. So on the diagram, we can say that there is going to be a normal reaction force at A, which is RA due to the pivot. And similarly at C, there is also going to be another normal reaction force, which is going to be RC due to the pivot. And since the plank is uniform, which means that the center of mass is located exactly at the midpoint of AB, which is going to be here. So this is going to be 15g, which is the weight of the plank. As we know that weight is equals to mg, where m is the mass and g is the gravitational acceleration, where g is equals to 9.81 or 9.8 in m1 meter per second squared. So we can say that this distance is going to be 2.5 meters as it is the midpoint of the plank. So we can take moments from A to cancel out the effects of RA. Therefore, the total clockwise moment is going to be equals to the total anti-clockwise moment because the system is in equilibrium. Therefore, we can say that due to this mass, or rather this weight, which is 15g, there will be a clockwise moment in this direction, which will be displayed in red. And similarly, in the anti-clockwise direction, the normal reaction force at C is going to provide that moment to occur. So therefore, we can say that the total clockwise moment is going to be 15g multiplied with the distance 2.5 meters, because we know that moment or torque is going to be equals to force multiplied with the perpendicular distance from the pivot. So this is going to be equals to RC, which is the force, multiplied with the perpendicular distance, which is going to be the distance from A to C, and is going to be 3 because the whole plank is 5 meters. And since CB is 2 meters, so therefore AC is going to be 3 meters. So rearranging for RC, we can say that RC is equals to 15G multiplied with 2.5 divided by 3. And placing G is equals to 9.8, we get 122.5 newtons as the value for RC, or the normal reaction at C. For number B, a person of mass 15 kg stands on the plank at the point D and it remains at equilibrium. The reactions on the plank at A and C are now equal. So we have to find the distance AD, and we're given that the reactions at plank A and C are now equal. So therefore we can say that the value of the normal reaction forces are going to be R. And similarly at D, there will be a downward force or weight of 45G. So we can resolve vertically and say that the total upward force, which is going to be R plus R, is equals to the total downward force, which is going to be 45g plus 15g. So therefore 2r is going to be equals to 60g, and finding the value of r, we get 30g newtons. Now we can take moments from A again and say that there will be a clockwise movement from 45g similarly to 15g. So we can say that 45g multiplied with the distance, which is AD, that we do not know yet, plus 15g multiplied with 2.5, which is the perpendicular distance from the center of the gravity to the point A, just like before here, which is going to be equal to the anti-clockwise moment, which is being caused by the normal reaction at C. So it's going to be R multiplied with the perpendicular distance, which is also going to be 3, just like before. So 45g into AD is going to be equals to 3 into R, which is 30g minus 15g multiplied with 2.5. So therefore AD is going to be equals to 7 by 6 meters, or approximately equals to 1.17. And this is our answer. For number 9, a uniform beam AB has weight W newtons and length 8 meters. The beam is held horizontal in a position where it is in equilibrium by two vertical light inextensible wires attached to the beam at the points A and C, where AC is equals to 4.5 meters as shown in a diagram. A particle of weight 30 newtons is attached to the beam at B. So we have to show for number A that the tension in the wire attached to the beam at C is equals to 8 by 9 W plus 160 by 3 newtons. So let us first draw the diagram to make it easier for us to understand the scenario. So this is going to be A, this is going to be C, and this is B. This distance is 4.5, and this whole distance AB is going to be 8. Similarly, there will be weight of the whole beam, which is W, and since it is uniform, we can say that the center of mass will be exactly at the midpoint of AB. So this distance will be 4 meters, and there will be a tension at A, which is TA, and a tension at C, which is TC. And we know that there is a weight of 30 newtons attached to B. So this is going to be 30 newtons. So we have to find the value of the tension at C. So just like before, what we have to do is we have to take moments from A to cancel out the effects of TA. So we can say for number A, taking moments from A, the total clockwise moment is going to be equal to the total anti-clockwise moment. And now if you look at the directions, clockwise is going to be this. So this includes the 30 newtons as well as the weight, because they are both positioned in the clockwise direction. And similarly, the moment, or rather the only force that is opposing this moment, is going to be due to TC, or the tension at C, which is acting in the anti-clockwise direction. So therefore we can say that W multiplied with the perpendicular distance from A, which is 4, plus 30 newtons, which is the force at B, multiplied with the perpendicular distance, which is 8, is going to be equals to the total anti-clockwise moment, which is due to tension at C, multiplied with the perpendicular distance, which is going to be 4.5. So therefore, tension at C is going to be 1 by 4.5 of 240 plus 4W. And if we divide the numbers like this, 240 divided by 4.5 plus 4 divided by 4.5, we can actually get 160 by 3 plus 8 by 9 W which can be rearranged to be written as 8 by 9 W plus 160 by 3 newtons. For number B, we have to find, in terms of W, the tension in the wire attached to the beam at A. For number A, we found that the tension at C was 8 by 9 W plus 160 by 3 newtons. So therefore, for number B, if we just draw the diagram again, here was A with a tension of TA. Similarly, this is C, where there was a tension at C, which is TC, and this is B. And we also had the distance of AB being 8 meters, and the distance of AC being 4.5 meters. Similarly, a particle of weight 30 newtons was attached to the beam at B, which was 30 newtons. Now we have to find the tension at A. So instead of taking moments from any place other than A, like for example, taking moments from C or B, we can simply resolve the forces vertically to find out the value of tension at A. So if we resolve vertically, we can say that the upper force, which is TC and TA, is going to be equal to the downward force, which is going to be 30 newtons, as well as the weight of the beam, which is W, which is exactly at the center of AB, because the plank or the beam is uniform. So resolving vertically, we can say tension at A plus tension at C, which is the upward force, is going to be equals to the downward force, which is 30 newtons plus W newtons. Now making TA the subject, we get TA is equals to 30 plus W minus tension at C, which is TC. So 30 plus W minus TC, which is minus 8 by 9 W plus 160 by 3. So we have to put brackets because this is the value that you have gotten here. So 30 minus 160 by 3 plus W minus 8 by 9 W, which is simply going to be 1 by 9 W minus 70 by 3 newtons. And this is the answer for B. For number C, it's given that the tension in the wire attached to the beam at C is 12 times the tension at the wire attached to the beam at A. We have to find the value of W. To solve number C, we have to express a mathematical equation that describes the statement that is being made. So it said that the tension in the wire attached to C is 12 times the tension in the wire attached to the beam at A. So we can say that the tension at C is going to be 12 times, so 12 multiplied with the tension at A. So we can just substitute the expressions in terms of W to get 8 by 9 W plus 160 by 3 being equals to 12 whole multiplied with 1 by 9 W minus 70 by 3. So multiplying both sides with 9, we get 8W plus 480 equals to 12 multiplied with W minus 210. And then continuing with the expression, we get 8W plus 480 on the left hand side. And similarly 12W minus 2520 on the right side. So we can further simplify and collect the terms on one side to say 12W minus 8W being equals to 480 plus 252. Therefore, the value of W is simply going to be 3000 divided by 4, which is 750. And this is the value of W. Now let's move on to centers of mass. So far, you have considered only uniform rods where the center of mass is always at the midpoint. If a rod is non-uniform, the center of mass is not necessarily at the midpoint of the rod. Rather, it could be in any place except for the midpoint of the rod. You might need to consider the moment due to the weight of a non-uniform rod or find the position of its center of mass. So now let's do some maths from the M1 book, which is from exercise 8D. In number 5, a plank AB has mass 24 kg and length 4.8 meters. A load of mass 15 kg is attached to the plank at the point C where AC is equals to 1.4 meters. The loaded plank is held in equilibrium with AB horizontal by two vertical ropes, one attached at A and the other attached at B as shown in a diagram. The plank is modeled as a uniform rod, the load as a particle, and the ropes as light inextensible strings. For number A, we have to find the tension in the rope attached at B. So if we just annotate on a diagram, here we have a tension at A, which is going to be TA. Similarly, a load is attached to the point C, which is 15 kg. Therefore, the mass will be 15g. As we know that weight is equals to mg, where m is the mass of the object. Similarly, there will be a weight acting at the center of AB, which is going to be 24g because of W is equals to mg, because the plank is modeled as a uniform rod, and there will be a tension at B, which is going to be TB. So because we have two tensions here, in order to find TB, we have to take moments from A. So taking moments from A, we can say that the total clockwise moment is equals to the total anti-clockwise moment. And if you look closely, the clockwise moment which goes in this direction is being caused by 15g, which is in this direction. Similarly, 24g also causes a clockwise moment. And to oppose that moment and to make sure that the system is in equilibrium, the tension at B acts in the opposite direction, which is the anti-clockwise direction that provides the total anti-clockwise moment. So therefore, we can say that the total clockwise moment is 15g multiplied with the perpendicular distance from that point, which is going to be 1.4 meters, plus 24g, which is the weight of the plank, multiplied with the distance, which is going to be at the center or the midpoint. And since the total length was 4.8, this is going to be 4.8 divided by 2 because it's the midpoint. So it's going to be 2.4 meters. So 2.4. And this is going to be equals to the total anti-clockwise moment, which is, as I discussed, going to be due to the tension at B multiplied with 4.8. So rearranging for TB, we can say that it's going to be 15g multiplied with 1.4 plus 24g multiplied with 2.4 and whole divided by 4.8. And using the calculator, and g is equals to 9.8, we can say that tension at B is roughly equals to 160 newtons, which is three significant figures. Now, in number B, the plank is now modeled as a non-uniform rod. With the new model, the tension in the rope attached to A is 25 newtons greater than the tension in the rope attached at B. So we have to find the distance of the center of the mass of the plank from A. So if we draw this diagram again, we can see that this is going to be tension at A, and this is going to be tension at B. This is AB, and this is the point C, which is 1.4 meters away from A. And this also has a weight of 15g, just like before. Now, we don't know the distance from the center of mass, so let's assume that this distance is going to be x, which is the required distance, and the weight is going to be 24g, just like before. Now, they said that tension at A is 25 newtons greater than the tension in the rope attached to B. Therefore, if we wanted to express this in a mathematical equation, we have to think about which quantity is more greater compared to the other. So if you compare tension at A and tension at B, you're going to think that the value of tension at A is going to be larger than the value at tension at B. because it said that the tension at A is 25 newtons greater. And now if I wanted to take the difference of both these tensions, then we would realize that the difference is going to be 25. So therefore we can make tension at A the subject and say that TA is equals to 25 plus tension at B. And this is an expression of tension at A in terms of tension at B. So now, in order to find the value of the tensions, we have to resolve vertically, just like in the previous question. So if you think about the forces acting vertically in the upward direction, we have tension at A and tension at B. And in the downward direction, we have the two weights, which is 15G and 24G. So resolving vertically, the total upward force, which is going to be tension at A plus tension at B, is going to be equals to the total downward force, which is 15G plus 24G. So simplifying and placing the expression for TA in terms of TB, we can write that 25 plus TB, which is the tension at B, plus tension at B is going to be equals to 15G plus 24G, which is going to be 39G. So further simplifying, we get 2 multiplied with the tension of B is equals to 39G minus 25 newtons, and therefore solving for TB we get 39G minus 25 whole divided by 2, and this will be equals to 178.6 newtons. Now we can take moments from A, and taking moments from A, we can say that the total clockwise moment is equals to the total anti-clockwise moment which, using the diagram, we can say that the clockwise moment is being driven by 24G in this direction as well as 15G in this direction, and the anti-clockwise moment is being provided by the tension at B, which is in this direction. So therefore we can say that 15G multiplied with the perpendicular distance from the pivot, which is 1.4, plus 24G multiplied with X, which is the distance that we don't know, being equals to tension of B, which is 178.6 multiplied with the perpendicular distance, which is going to be 4.8 meters. Now solving for X, we can say that 24Gx is equals to 178.6 into 4.8, which is going to be 257.28, subtracted by this, which is going to 205.8. Therefore X is going to be this expression divided by 24G, which is going to be equals to 2.77 meters. In number 7, we have a non-uniform rod AB of length 25 meters and weight 80 newtons resting horizontally in equilibrium on support C and D as shown on a diagram. The center of mass of the rod is 10 meters away from A. A particle of weight W newtons is attached to the rod at a point E, where E is X meters from A. The rod remains in equilibrium and the magnitude of the reaction is 5 times the magnitude of the reaction at D. We have to show that W is equals to 400 divided by 25 minus 3x. So we can say that this is going to be the reaction at C and this is going to be the reaction at D, because it's given that the reaction at C is 5 times the reaction at D. Therefore we can mathematically make an equation saying RC is equals to 5RD. Therefore we can resolve vertically, and because the weight is going to be nearby C as the reaction force is much more greater, so this is going to be 80 newtons, and it's given that the center of mass of the rod is 10 meters away from A, so this is going to be 10 meters, and it said that a weight of W newtons is attached to the rod at a point A, which is X meters from A. So therefore we can also say that this is going to be here, where this distance is X and the weight is going to be W. So resolving vertically, the upward force, which is RC plus RD, is going to be equals to the total downward force, which is W plus AT. Now we can substitute the expression for RC is equals to 5RD and write 5RD plus RD is equals to W plus AT. Therefore 6RD is equals to W plus 80, and so RD is equals to W plus 80 whole divided by 6. And similarly we can create an expression for RC, which is going to be 5 times of that. So it's going to be 5 divided by 6 whole multiplied with W plus 80. Now if we take moments from A, we can see that there will be a weight W, there will be 80 newtons here, similarly a reaction at C and a reaction at D. So because this is the distance X, this is 6 and this is 10, and the distance from A to D, which is shown in red, is going to be the whole length of AB minus this 5. So it's going to be 25 minus 5, which is 20 meters. So taking moments from A, we can say that the total clockwise moment is equals to the total anti-clockwise moment, because the system is in equilibrium. Therefore taking moments from A, we can say that the total clockwise moment, which is being provided by 80 newtons in this direction, and similarly by the weight, which is W, in this direction. So 80 multiplied with the perpendicular distance, which is going to be this distance, and this is 10, plus W multiplied with its perpendicular distance from the pivot, which is going to be X, is equals to the total anti-clockwise moment, which is due to RD multiplied with 20 meters, because it is a distance of 20 meters from A, plus the reaction force at C, which is RC, multiplied with the distance 6. So simplifying, we get 800 plus WX is equals to RD, which is W plus 80 divided by 6 multiplied with 20, plus 5 by 6 multiplied with W plus 80 into 6. So therefore we get 800 plus WX is equals to 800 by 3 plus 10 by 3W plus 5W plus 400. Now further simplifying and multiplying both sides with 3, we get 2400 plus 3WX is equals to 800 plus 10W plus 15W plus 1200. And now gathering all of them in one place, we have 2400 minus 800 minus 1200 being equals to 25W minus 3WX. So on the left hand side we have 2400 minus 800 minus 1200, which is going to be 400, being equals to 25W minus 3WX. So we can take a common factor of W and get 25 minus 3x. So making W our subject, we get 400 divided by 25 minus 3x, and this is what we had to show. So now let's move on to the last concept of moments, which is tilting. You need to be able to answer questions involving rods that are on the point of tilting. When a rigid body is on the point of tilting about a pivot, the reaction at any other support or the tension in any other wire or string is zero. For example, let's say if I have a plank that is being balanced by two pivots A and B, and let's say I have placed a mass close to the edge of A, and if this will be on the point of tipping about A, then the reaction at B will be 0. Similarly, in our alternative case, if a mass is placed nearby B at the edge of the plank, and if the plank is going to tilt about B, then the reaction at A will be 0. So let us do a question from exercise 8E of number 7, where it's given that a uniform beam AB of weight WB and length 14 meters hangs in equilibrium in a horizontal position from two vertical cables attached at points C and D, where AC is equals to 4 and BD is equals to 6. A weight of 180 newtons is hung from A and the beam is about to tilt. So when we place a weight of 180 newtons, the tension at D is about to be 0. And similarly, the weight is removed and a different weight V newtons is hung from B and the beam does not tilt. So this is a key word. So we have to find the maximum value of V. So in our first scenario, when we placed a mass, or rather a weight of 180 newtons at A, the whole system was about to tilt. So this means that the tension at D when the weight was placed is 0, meaning that the wire was slack. So there will be a tension at C, and similarly, because this is a uniform beam, there will be a weight W, which is exactly at the midpoint of AB, which is 7 meters. So we can resolve vertically again and say that the total upward force is equals to the total downward force, which is TC, is equals to 180 plus W. And taking moments from A, we can say that the total clockwise moment is equals to the total anti-clockwise moment. Here in this case, the clockwise moment is being provided by this force only, because we have assumed that this is the pivot. So the effect of 180 newtons is going to be 0, or rather the turning effect will be 0, and the force that is acting opposite to the direction of W is providing the anti-clockwise moment in this direction. So therefore the clockwise moment is going to be W multiplied with the perpendicular distance, which is at 7 meters, as I've said, because this is a uniform beam, is equals to the tension at C multiplied with 4, because this distance is 4. So therefore we can find the value of W using this expression from earlier. So 7W is equals to 4 multiplied with 180 plus W. So simplifying, we have 7W is equals to 4 into 180, which is 720, plus 4W, and therefore simplifying for W, we have 7W minus 4W is equals to 720. Therefore 3W is equals to 720, and so W is equals to 720 divided by 3, which is going to be 240 newtons. Now if we consider the second case, where when they placed a weight V at B, the system was about to tilt again, meaning that the tension at C was 0 at this moment. So TC is 0 and tension at D is something that we don't know, but we will find out. Similarly, this is going to be W, which we have found using this expression before, which is 240, and this will be a distance of 14 meters from A. This will be a distance of 7 meters, and this will be 8, because 4 plus 4 is 8. Now we can take moments from A and use the same principle that the total clockwise moment is equals to the total anti-clockwise moment. So therefore we can say that the clockwise moment are being provided by these two forces. So V multiplied with 14 plus W, which is 240, multiplied with the perpendicular distance, which is 7, being equals to the tension at D multiplied with the perpendicular distance, which is 8. Now if we resolve vertically again, just like before, we can see that the tension at D is equals to 240, which is the downward force, plus V, which is another downward force. So therefore we can substitute that in our equation, finding 14V plus 240 into 7, which is 1680, being equals to 8 multiplied with 240 plus V. And now simplifying, we get 14V plus 1680 being equals to 8 multiplied with 240, which is 1920, minus 8V. So further simplifying and collecting all of the terms on the left side, we have 14V plus 8V is equals to 1920 minus 1680. So 6V is equals to 240. Therefore V is going to be equals to 240 divided by 6, which is 40 newtons. And this is our answer. Thank you all for watching the video. This is the end of Mechanics 1. Please make sure to leave a like, comment, share and subscribe if you enjoyed the content. If you have any specific video requests or ideas, feel free to comment down below. See you guys in the next video. Goodbye.